Hi there, this is Mrs. Petranis for our second chemistry review session. Ms. Blunt left off with gram formula mass, so that's right where we're going to pick up. Gram formula mass is also known as molar mass, and it is the mass of 1 mole of any substance. So to figure out the mass of 1 mole of any substance, we need to use our periodic table to look up the masses of each of the elements in our compound. So if we look up calcium on our periodic table, it has a mass of 40.08. I'm going to round that off to 40. Oxygen has a mass of 16, and hydrogen has a mass of 1. So if I add this all up, I have 40, because there's only 1 calcium. There are 2 oxygens, so I'm going to do plus 2 times the 16 for oxygen, and there are also 2 hydrogens. So I will add 2 of the hydrogens in. That will give me a total of, can't do this math in my head quickly, 94 grams per mole. This label means that there are 94 grams in 1 mole of the substance. So we're going to use gram formula mass to help us solve other problems relating to moles. So moving on to our next slide. So we need to use our mole calculations formula to represent or to figure out problems. Hold on a second. To figure out problems that have to do with mole calculations. So on table T, mole calculations, the mole calculations equation is given to us. Okay, it's the number of moles is equal to the given mass over the gram formula mass. Remember, we just solved for the gram formula mass by adding up all of the masses of each element in a compound. So we need to use that gram formula mass when we're solving mole problems. So our next problem here says that we have 0.30 moles of NaHCO3. Now, it wants us to express this in grams, so we're going to use our mole conversions equation. So if I want to express this in grams, I have my 0.30 moles is my number of moles is equal to, I'm not given a mass. There's no mass in this problem up here, so I'm going to change that into x. And my gram formula mass, I need to add up all of the masses of my elements in NaHCO3. So Na is 23, plus we have 1 hydrogen, so I'll say plus 1. We have 1 carbon, and each carbon is 12. And we have 3 oxygens. Each oxygen is 16. So if I figure out my molar mass here, 23 plus 1 plus 12 plus 3 times 16, I get a total mass of 84. So I'm going to put that gram formula mass on the bottom of my problem. So to solve for x here, the easiest thing to do is I'm going to put my 0.30 over 1, and I'm going to cross multiply these two. Okay, so 0.3 times 84 is equal to 25.2 grams. Okay, and if you think about this, 84 is the mass of 1 mole. So if I have only 0.3 moles, I want to multiply the two values together to give me what the mass of 0.3 moles is going to be. To express a grams down here at our bottom problem, to express a mass and change it to moles, we can use the same mole conversion problem that we used before. So I don't know my number of moles, that's the question. And I have a mass given to me here of 62.3 grams. And I need to put it over the gram formula mass. Remember, we always know the gram formula mass from adding up the masses of each element in the compound. So magnesium has a mass of 24, and fluorine has a mass of 19. We have 2 of those fluorines, so I do 2 times the 19. So 24 plus 2 times 19 gives me 62. So I'm going to put that mass on bottom. I can see right now that this is going to be really close to 1 mole. So if I do 62.3 divided by 62, I'm going to get 1 point, lots of numbers here, 004. Now you may ask yourself what to round to. You guys always ask this question. So if you think about what information we're given in both of these problems, back up here to the first one, my 0.30 moles has 2 significant figures in the value. So I'm going to round my answer to 2 significant figures, so it would be 25 grams. If we look at the second problem, my given information was 3 significant figures, so I want to round off my final answer to 3 significant figures, which would be 1.00, and we are calculating the number of moles here. Okay, moving right along. Continuing with our math in chemistry, another type of problem that you're going to have to solve is percent composition. Okay, we recognize these problems because they always talk about percents. So table T does give us an equation for percent composition by mass, where it's the mass of the part over the mass of the whole times 100. Okay, this can be used for regular percent composition problems, and it can also be used for hydrate problems. So for our first problem, it says to find the percent by mass of nitrogen and NH4NO3. So this is kind of a tricky problem because nitrogen appears twice in this formula, although it looks like it's once. So if we take a look, the first step we want to do is to find the mass of the whole thing. So to figure this out, we have nitrogen. There are 2 nitrogens in this formula, so we do 2 times 14, plus there are 4 hydrogens. Each hydrogen has a mass of 1, and then there are 3 oxygens. Each oxygen has a mass of 16. If I calculate this out, 2 times 14 plus 4 plus 3 times the 16, I get a mass of 80 grams per mole. Now, if I want to figure out the percent by mass of nitrogen, I only want to look at the part that is nitrogen, which is right here. 2 times 14 is going to be 28. So I'm going to put my information into my percent composition formula. So my mass of my part is 28, and the mass of the whole compound is 80. And then I want to multiply by 100. Make sure when you're showing your work, you show the entire setup. Don't assume that we know that you're multiplying by 100. All of the numbers should be part of that setup. So if I do 28 divided by 80, I'm going to hit enter on my calculator, and then I'm going to put times 100 after I hit enter, and I get 35%. For the next problem, this is a hydrate problem. I know that this is a hydrate because this is a hydrate formula. Now there's a little mistake in the way that the font was formatted. This little dot here should actually be up in the middle, so it looks like multiplication. But to find the total mass of the hydrate, we don't actually multiply the 2 formulas together. We add up the total mass of the entire formula. So if we look, I'm going to erase this here. If we look at CaSO4, we want to figure out how much of it is just the water. So I'm going to look at one piece at a time. My calcium has a mass of 40. Sulfur has a mass of 32. And I'm going to do these oxygens separate from the oxygens that are in water because it will help me for my math later. So I have 4 oxygens. And I'm going to add to it my water molecules. Now if we look at H2O, hydrogen each has a mass of 1, and oxygen has a mass of 16. So each water is 18 grams. So I'm going to, while I'm adding it into my total, I'm going to just add it as a whole water molecule. So I'm going to do 2 times 18 for that water. So if I put this in my calculator to get my total mass, 40 plus 32 plus 4 times 16 plus the 2 times that 18 for water, I'm going to get 172 as the mass of the whole compound. So if I want to know just the percent by mass of the water, I'm going to look at just that water piece, which is 2 times 18. That's 36 grams. And I'm going to take the 36 grams divided by 172, which is the mass of my whole compound, and I'm going to get times 100, 20.9%. Okay, so to remember, for hydrates, you only want the mass, the part that you want is the mass of the water divided by the mass of the whole hydrate. Moving right along, to find molecular formulas from empirical formulas, we have a process, because to go from a molecular formula to empirical formulas, we just reduce. But if we want to go backwards, if we are given an empirical formula and we want to change it to the molecular formula, we have a step-by-step process we can use. So if we read our problem, a compound has a molecular mass of 180 AMU. So this is my molecular mass. And an empirical formula of CH2O. What is the molecular formula? So what this is telling me is, remember, empirical means this is a reduced formula. It's our lowest ratio. So this question is actually asking me to unreduce it. So if I take my CH2O, the first step is that I want to find the mass of the empirical formula. So to do that, my empirical formula is CH2O. The hydrogen is 12. The carbon is 12. There are 2 hydrogens. They're each 1. And oxygen is 16. That gives me a total mass of 30. So one empirical formula has a mass of 30. I want to know how many empirical formulas will fit in this 180 AMU. So my second step is I'm going to divide the molecular mass by the empirical formula mass we just found. So I would take the 180, which was given to me in the problem, and divide it by 30, and that would give me a nice whole number of 6. So I'm going to take this 6 and multiply all of my subscripts in CH2O by that factor of 6. This is the 6 is really telling me how much I reduced my original formula by. So I'll take my C, which was 1H2O, and multiply them each by 6, and I would get C6H12O6, which is my molecular formula. If I divided it all by that factor of 6, then I would get back to my empirical formula. Now we're moving on beyond the math, and we're going on to some more conceptual parts of chemistry. And we started out the year this year comparing physical properties and changes to chemical properties and changes. Now remember, properties are the same as characteristics. So we are not talking about changes made to the substance. We're just talking about what properties that they have. Okay, so physical properties are going to be characteristics that are observed without changing the substance. Now, when I say without changing, I really mean without changing its identity or what the substance is. So when we think about physical properties, we can observe them about any substance. So an example of a physical property, something we can observe without changing, might be boiling point. Boiling point, we could boil a substance, which would actually be the change, but the boiling point is going to be the temperature at which it boils. We can observe it. It doesn't change what the substance is. It just is a characteristic that's observed. Another example would be density. And we can also think of basic physical properties like that we would observe with our five senses, appearance, color, texture, smell, shape, examples like that. Where physical changes are going to be where the matter is actually changing form. So this is more of an action. So physical changes are going to be changes to a substance that do not change its identity. When I say identity, I mean what the substance is, what its name is, what its formula, what it's made of. We want to change it, but we don't want to change the actual substance. So an example of a process that is physical would be any type of phase change. Phase changes do not, like for example with water, if we melt ice, water is still water. It does not break bonds. The only thing that changes during physical changes would be things like intermolecular force. So some examples of phase changes would be boiling, freezing, where the substance still stays the same identity, but it does not change into a new substance. Another example of a physical change would be dissolving substances. Dissolving does not change the identity of a substance, it just breaks it down into smaller pieces. Now, chemical properties are going to, we can kind of use the same definition that we have over here. Instead of observed without changing the substance, we can observe this by changing its identity. So observed by changing the identity of a substance. So if we were to put a substance through some changes and the identity was changed, such as if we tried to set something on fire and it did catch on fire, the property would be that it is flammable. Okay. A common chemical property is whether a substance is reactive to another substance. Now keep in mind what we wrote up here is that things that have similar chemical properties. Sorry. Things that are in the same group on the periodic table are going to have similar chemical properties. That's why they're grouped together. And remember, groups are the columns on the periodic table. So everything in, for example, group 17, we call the halogens. They're all going to be highly reactive. They all have similar chemical properties. Now, the chemical changes are what the process would actually be to change a substance's identity. So changing one substance to a new substance. Chemical changes usually involve breaking and forming bonds. So if we were to think about what this looks like in a molecular form, if we had two separate elements, A and B, a chemical change would be maybe a bond forming, between these two elements. So A and B would come together to form AB, which is a bonded substance. Where a physical change would be maybe we have A and B that are separate, but then we could just put them closer together, but not bonded. So it's just a physical change. This would be an example of condensing these substances. Sorry, this is getting a little messy here. This would be condensing the substances, where A plus B over here, we're actually forming a bond. So it's going to be a chemical change. Some examples of chemical changes. We said flammable was a chemical property. The change that would need to go through to test if something was flammable would be burning something. Okay? Or reacting a substance to another substance. For example, metal with acid would be an example of a chemical change. So you should be able to kind of see a list of different changes and be able to identify what are chemical changes and what are physical changes. Moving right along. Actually, we're going to stop here and we're going to pause and we're going to go on to our next session.